Here in this video, we're going to talk about electrochemical gradients and what forces act upon an ion. So, if we draw a cell, and we typically say we're going to have a substance outside of the cell, the substance inside of the cell, right? We often are under the assumption that something will move following its concentration gradient. But let's, for the sake of our example, let's say that there is a high concentration of sodium on the outside. There is a low concentration of sodium on the inside, and there is a channel for sodium. So one of the things that we have to remember is that salts form ionic bonds, and then they can dissociate into their individual ions, right? And so because of that, they are going to have a charge with them. Ions will have a charge with them, okay? So if we have a high concentration on the outside and we have a low concentration on the inside, we're going to say that that substance, or that molecule, that ion, is going to want to move from an area of high concentration to an area of low concentration, following its concentration gradient, right? And so there is a force acting on it moving in this direction with, let's say, this magnitude, and this is based off of concentration. Okay? So what happens, though, if I take and I put some more stuff inside of this cell, and we won't say what it is, but just generically, we're going to say that whatever it is, it has a positive charge. And we put a whole bunch of positively charged things inside of this cell, right? And so with that positive charge, right, how do you think that that might interact with a positively charged thing trying to come into the cell, right? So like our positively charged ion. Well, those two things are going to repel each other, right? That positive charge inside of the cell is going to repel the positive charge of the ion. So in actuality, there's also a force acting in this direction, right? And this is based off of charge, okay? Now, let's say we put a whole bunch of more sodium outside of this cell, and we really increase that force of the concentration gradient, like so, all right? And if we look at this, if we add these two forces together, kind of like we did with osmosis, right? We have a net force in this direction with this magnitude, right? So that's the net force, right? So what we have is we have a chemical gradient that's here in blue, known as the concentration gradient, but we also have a charge gradient, and that's the electrical gradient. So this down here, this net force, that is what we're going to refer to as the electrochemical gradient. Okay? And that electrochemical gradient is what's going to drive the movement of those ions. Okay, so we have to account for both the concentration gradient and we have to account for the chemical gradient, that charge gradient. Okay, so what happens if, let's say, we take this, and let me move my screen up a little bit, and we'll draw another cell. We're going to do the same thing. We're going to put a high amount of sodium on the outside. And we are going to put a low amount of sodium on the inside. We'll put in a sodium channel so that sodium can move through the membrane. Okay. And we will put a same amount of positively charged stuff on the inside. Like so. Right? Now, our forces look like this again. There's like this for concentration, for this versus electrical gradient. Now, when sodium moves into the cell, right, what's it going to do? It's going to take its positive charge and take with it, right? So what happens is as it takes its positive charge with it, that positive charge, that positive force pushing back is going to increase, right? So eventually we're going to get to a point where we have no net force, okay? And that no net force is because the concentration force or the chemical force is equal and opposite to the electrical force, right? So when those two things are equal and opposite, right? So we'll say chemical gradient is equal and opposite which means that there's no net force. That is what we call the equilibrium potential of an ion. The equilibrium potential. Some people will also refer to this as a reversal potential, and they call it a reversal potential because as we continue to build up that positively charged ion on the inside of the cell here, right, eventually we can get to a point where we could reverse the net force, right? And so that's why we call it the reversal potential. Okay, so now we know what the gradients or the forces acting on an ion are, and we know when these ions will reach equilibrium, right? They will move to a point where they reach equilibrium where the equilibrium potential is reached, or where that chemical gradient is equal and opposite to that electrical gradient. So make sure that you understand that before you watch the next video on equilibrium potentials and how equilibrium potentials can be used to determine the directional flux of a given ion.